Hello everyone. Today we are going to study about temperature stresses. Temperature or thermal stresses are the stresses induced in a body due to change in temperature. Let us see the definition for the coefficient of linear thermal expansion. It is defined as the change in length per unit length per degree change in temperature. Alpha is equal to change in length per unit length and per degree change in temperature. In this equation, alpha is the coefficient of linear thermal expansion, L is the original length, delta L is the change in length, delta T is change in temperature. Let us consider a bar AB. In the first figure, the bar is constrained at both of the ends. Let us assume that the temperature of the bar is increased by delta T. We know that in the first figure, the bar is constrained. Suppose the bar is free to expand due to the increase in temperature. There will be change in length delta L. We know that in the first figure, the bar is constrained. So there will be no change in length even the temperature is increased, because here there will be a force to prevent the change in length. Here we can come to the conclusion the restraining force P should be equal to the force producing change in length. Here we can use the formula for the change in length delta L PL upon AE. Here we can take L on the left side, so it will come in the denominator. Initially we have formed this equation. We can take delta T on the left side, so we will get delta L upon L is equal to alpha into delta T. For delta L upon L, we can use alpha into delta T. We know that stress is equal to load by area. Here P upon A is the thermal stress. Then let us take E on the left side. Finally, we have formed a formula. Thermal stress is equal to alpha into delta T into E. We know that Young's modulus E is equal to stress by strain. So strain is equal to stress by E. Using that concept, we can find thermal strain, which is equal to alpha into delta T. Now let us find the stress and strain when there is yielding. Let us assume that the supports of the bar can move by a distance of delta. In the figure, you can see that the bar yields at a distance of delta. We know the formula for the strain, that is actual expansion by original length. This is the actual expansion. The actual expansion is equal to delta L minus delta. From this expression, we can get delta L, which is equal to alpha into delta T into L. So delta L minus delta is equal to alpha delta T L minus delta. For the actual expansion, let us apply this. This is the formula for the actual strain. We know that E is equal to stress upon strain. So stress is equal to strain into E. When we multiply this with the E, we will get actual stress. Now we are going to derive the formulas for the thermal stress in the stepped bars. Let us consider a stepped bar having two parts, part 1 and part 2. Let L be the length of the stepped bar. L1 and L2 are length of the first and second parts. E1 and E2 are the Young's modulus of the first and second parts respectively. Alpha 1 and alpha 2 are the coefficient of linear thermal expansion of the first and second parts respectively. The total change in length delta L should be equal to the change in length in the first part plus the change in length in the second part. Previously, we have formed an expression for delta L. Let us apply that. Here we have separate alpha and L values. Delta T is same. Let us take it outside. We know that stress is equal to load upon area. Stress in the first part is equal to load upon area 1. The stress in the second part is equal to load by area 2. So in the first part, P is equal to sigma 1 area 1, and in the second part, P is equal to sigma 2 area 2. In both of the parts, the value of P will be same. So we can equate these two values. Sigma 1 A1 is equal to sigma 2 A2. Then we can take A2 on the left side. It will come in the denominator. We know that E is equal to stress by strain. So strain is equal to stress by E. For the first part, strain is delta L1 upon L1. Stress is sigma 1. Young's modulus is E1. Let us take L1 on the right side. So for delta L1, we will get sigma 1 L1 upon E1. In the similar way, for delta L2, we will get sigma 2 L2 upon E2. For sigma 2, we can apply A1 upon A2 into sigma 1. Let us add delta L1 and delta L2. Here sigma 1 is common. Let us take it outside. For delta L1 plus delta L2, we have already made one expression, and now we have made one more expression. Let us equate both of the expressions. You can see that I have equated both of the expressions. For these two terms, we can take LCM. Then let us take this term on the right side. It will come inversely. This is the formula for sigma 1. We know that sigma 2 is equal to area 1 upon area 2 into sigma 1. Let us multiply sigma 1 with the area 1 upon area 2. Area 2 will be eliminated. Finally, for sigma 2, we will get these. In these two formulas, all of the values will be same except the areas in the numerator. For sigma 1, there should be area 2, and for sigma 2, there should be area 1. This is the only difference in these two formulas. Suppose the Young's modulus are same and the values of alpha are same. We can simplify these two formulas like this. Suppose the cross section is uniform, area 1 and area 2 will be equal to A. We can take A outside, L2 plus L1 becomes L. Area will be eliminated and L will be eliminated. Finally, for sigma, we are getting alpha into delta T into E, which is the same formula we have derived initially for the uniform cross section. Now let us derive the formulas when there is yielding. Let us assume that the supports of the stepped bar can move by a distance of delta. So delta L is equal to delta L1 plus delta L2 minus delta. For delta L1 and delta L2, we have made the expressions. Let us apply them. In the previous derivation, for delta L, we have made this expression. Now for delta L, we have two expressions. Let us equate both of them. Here delta 1 is common. Let us keep it outside. For these two terms, we can take LCM. Then we can take this term on the right side. So it will come inversely. This is the formula for sigma 1. We know that sigma 2 is equal to area 1 upon area 2 into sigma 1. For sigma 1, we can apply this formula here. Then we can eliminate area 2. Finally, we will get the formula for sigma 2. Suppose the Young's modulus are same and the values of alpha are same. We can simplify these formulas like this. If the cross section is uniform, area 1 and area 2 will be A. Area can be taken outside and can be eliminated. L2 plus L1 is L. Finally, we will get this formula. This is the same formula previously we have made for the uniform cross section. Now we are going to end this session. Thank you for watching this video.